Thanks for the introduction and for inviting me. The subject of my discussion is dark matter. This is a topic which came into forefront in the context of some astrophysical issues as well as issues dealing with the universe at large. However, this very fact that there is dark matter poses a rather stiff challenge to those who delve in the physics of elementary particles, that is to say, the fundamental constituents of everything in the universe. And it is on this aspect that I'll concentrate, although in a brief, sketchy, and non technical manner. Now, it is an undeniable fact now that the energy, as far as the contribution to the energy density of the universe is concerned, more than 5 times of contributions come from invisible massive gravitating objects rather than the visible particles consisting of all the elementary particles we know about. However, there is no unanimity as yet as to what dark matter could be made of. If it is, so to say, constituted of some unknown particles, that it implies immediately physics beyond the existing theory of elementary particles based on a certain symmetry group. Let's not talk about that. But it means some extension of the standard model, as it's called, in terms of particle content and perhaps in terms of interactions as well, fundamental interactions. But then, what kind of physics beyond the standard model is behind dark matter remains anybody's guess now. There are suggestions galore, but prediction or interpretation of observations in this respect often depend on certain assumptions and bias on our part, assumptions in the terms of particle physics as well as on astrophysical issues or parameters. In practice, therefore, possibilities can be more divergent than we naively think sometimes. Now, the existence of dark matter in the universe was indicated or suggested by a number of things. The rate of rotation of galaxies, detailed observations of the cosmic microwave background radiation, which is ubiquitous, then gravitational lensing in bullet clusters, formation of structures in the universe, and appearing and disappearing claims on observation of gamma ray signals, excess positrons, or antiprotons in cosmic rays, and so on and so forth. Just to give pictorial description, this is the galactic rotation thing, something which triggered the first speculations on dark matter, where we know from this high school level equation that the rate of rotation of a galaxy at a certain distance from its center is connected with the total mass contained within that distance. And here, for most galaxies, the observation tells us that the rotation rates as observed testify to much higher mass contained than what is provided by luminous matter within the galaxy. Similarly, these bullet clusters is a very strong hint in favor of dark matter being made of particles. Bullet clusters are basically the remnant of 2 galaxies which have collided, leading to some bullet-like extension. However, the interesting thing is that even if you go beyond the part of such bullet cluster structures, which is visible, even beyond that, you see gravitational lensing effect, that is to say, starlight bending under gravity, telling us that there is some actually localized, concentrated mass, which is obviously made of some particles hitherto unknown. Anyway, now a dark matter particle cannot participate in either electromagnetic or strong interactions, because then it would have led to the formation of supermassive atoms or super heavy nuclei in some corners of space, and the spectra of these would have been very characteristically seen, and spectroscopists have done such a wonderful job of such observations that there is no possibility of that kind. So the main possibilities among several others are those where dark matters are weakly interacting massive particle, or feebly interacting massive particle, WIMP or FIM, and the rest of the discussion will be around WIMPs only. Now, in all theoretical analysis or theoretical formulation of scenarios accommodating dark matter, and also in terms of explaining or rather interpreting data or predicting them, there are some bias and uncertainties involved. First, direct dark matter search has led to the setting up of many experiments across the globe, but there the expected event rates depend on the flux of dark matter around the Earth, and there we expect or rather assume that in most studies that the distribution of energy is answer to the distribution of so-called Maxwellian distribution and no local fluctuation or clumping. Then, when it is weakly interacting massive particles, it has been involuntarily assumed sometimes that the masses cannot be very different from a few hundred GeVs. When we turned on particle accelerators or colliders, like for example the Large Hadron Collider, we assume that the signals of dark matter will consist in missing momentum or energy because dark matter particles are invisible. Then it is assumed, not always, but involuntarily, as I said, is that dark matter necessarily is a stable particle. And last but not the least, when dark matter annihilation and decay is concerned, because they lead to what is called the relic density of the universe, where there are clear limits, that the annihilation of dark matter and decay when it takes place is into two particle final states. Now, departure from any of these standard assumptions, or more than one of the standard assumptions, will alter dark matter search paradigms in big ways, and also the standard conclusions of the analysis of data as well as prediction of scenarios. Now, our judgment, therefore, may be modified in some cases. I'll just talk about a few illustrations of this. First, a scenario of trans-TeV dark matter. Tera-electron volt is one order of magnitude above the scale at which weak interaction prevails, or rather the so-called phenomenon of electroweak symmetry breaking takes place. And due to some semi-speculative coincidence called the WIMP miracle, which I am not elaborating here, people thought the dark matter mass, WIMP dark matter mass, cannot exceed this mass scale. However, on a closer scrutiny, this doesn't kind of cut any ice. And in fact, there can be dark matter particles weakly interacting, which can be in multi-tera electron volt regions, all the way till close to 100 TeVs, where there are some theoretical problems of unitarity of scattering matrices, which can kind of can be jeopardized. However, for masses exceeding a TeV, any collider experiment like the Large Hadron Collider, which is the most energetic particle accelerator produced so far, is unlikely to see, almost it's impossible to see that. Also, the direct searches become ineffective because the rate of cross section of the ambient dark matter cloud with direct search experiments or detectors, this is a kind of elastic scattering process that we think of, there the rates fall rather miserably. Therefore, in such cases, for trans-TeV dark matters, one has to depend on indirect signals. Indirect signals consist of, as I said, gamma rays, cosmic ray studies, and so on. These have put certain limits. However, the regions of a dark matter parameter space that can be probed leaves certain regions unprobed as far as gamma ray signals, cosmic ray analysis, etc. are concerned. One possibility that has been widely studied recently is that of radio signals. Now, in certain galaxies of clusters where dark matter concentration is high, their pair annihilation may lead to directly or through cascade decays electron-positron pairs. These electrons or positrons undergo spiraling motion under galactic magnetic fields, in the process having several kinds of electromagnetic energy loss, but at the end, leading to synchrotron radiation. And the most pertinent synchrotron radiations that we'll talk about are in the radio range. So radio synchrotron signals turn out to be interesting possibilities if there is some stellar structure consisting of large dark matter concentration. The potential sources of this kind are dwarf spheroidal galaxies, examples being things like SEG1, Draco, Reticulum, Ursa Minor, and many others. These are in 10 to several tens of seconds, megaparsecs away from our Milky Way galaxy. Now, these dwarf spheroidal galaxies of large dark matter density, the star formation rates there are low, which makes backgrounds for spurious processes less disruptive. And what can be a problem are foregrounds or radio signals from some spurious source between us and the dwarf spheroidal galaxy. But these can be eliminated with the help of very high resolution radio telescopes. And one such telescope which is in the coming, is the Square Kilometer Array telescope, which is likely to start operation towards the end of the current decades, where you have dishes in South Africa as well as Australia. Now, some recent studies by us have shown that for dark matter masses in the 5 to 8 TeV range or even some 10 TeV ranges, radio telescope for many scenarios can lead enough and distinguishable signals rising well above the threshold of observability of the SK in the range 100 megahertz to 4 gigahertz mostly in something like 100 hours of observation. And this can make the parameter space of a dark matter scenario spanned by the mass of the dark matter and rate of its annihilation amenable to detection. This is a typical example of one particular scenario. I'm not going into details, where this is the mass of the dark matter. Against this, we plot the uh, annihilation rate. For any dark, sorry, what's happening? For any dark matter mass, this gives the maximum annihilation rate possible consistently with gamma ray data. Actually, these have been slightly improved of late, and these are the maximum annihilation rate consistent with observation, or rather non-observation of additional positrons or antiprotons in cosmic rays. We can clearly see that there is a big region which can rise above the threshold of detectability through SK, and once you are above this band, this shows the minimum. Why band? Because of uncertainties in astrophysical parameters. Two quantities that very significantly affect the radio synchrotron emission are the diffusion coefficient of the galaxy within the galaxy and the magnetic field of the galaxy, which is the all important quantity driving synchrotron radiation. Now, very qualitatively, I would like to rattle off the factors governing the radio flux for large dark matter mass, trans TeV mass. Of course, large annihilation that helps, but then on top of that, the spectrum, the rate of interaction, and the etc. matters. Basically, a large mass on one side suppresses rates but provides more phase space to the electrons that are produced in interactions, and therefore you have a larger supply of electrons which through certain electromagnetic processes are in the right ballpark of energy to emit large fluxes of radio signals. And of course, large diffusion coefficient will cause loss of electrons faster, and larger magnetic field will keep bigger, rather larger number of spirals within the galaxy, which will sustain radiation. So these are the two factors which are important. Okay, the two other topics that I quickly covered, and if the third one is not covered, it's not a problem, is mass limits on a WIMP dark matter. Now, some studies based recently on direct searches, indirect signals, various kinds, radio, neutrino, etc., and relic density observation from cosmic microwave background radiation indicate that waves up to something like 100 GeV is exceeding some, I mean, up to something like 100 GeV is very, very strongly restricted unless you have some very, very contrived models. However, there are also suspect. They are also suspect. For example, direct search limits as obtained through the sheer quantum mechanical calculation also make certain intrinsic assumptions which have sometimes been questioned. Then the indirect signals consisting of various kinds of things that I've already mentioned, they Uh, they depend on the annihilation branching ratios. When two dark matter particles are annihilating, what they go into, there some of our theoretical bias based largely on the standard model of particle interactions guide us, and therefore we are somewhat restricted in the listing of possibilities. If such bias is not there, it was shown by these people just before COVID broke out that a wind dark matter going down all the way to 10 dB is not at all ruled out or disfavored if you can allow, or rather allow, the possibilities of it decaying in many other ways. And when we were recovering from COVID, we showed that actually it is more unrestricted than that. There, in all studies, it has been sort of ignored that the dark matter particles can annihilate and annihilate dominantly into a pair of neutrinos. If that is allowed, and that is allowed to be large, then anything above something like 10 MeV can be consistent with all observations. And you cannot go down below 10 MeV in the present setup because that will affect the heavy element abundance rate, which is rather accurately measured and tampering with which will bring in a lot of new physics possibilities into which I am not going. So given all this, the branching, there is a region of the parameter space where you rule out the rate of annihilation of dark matter in certain ranges. And these are all to lie above this shaded dashed lines because that corresponds to the maximum relic density that you can have. However, if there are rates above that, they are constrained by various kinds of gamma ray, X-ray, etc. observations. And therefore, when neutrinos come in, they make some of the observed possibilities invisible, and therefore you have larger amounts of phase space opening. And if the neutrino branching ratio tends to be something like more than 99%, then any mass 10 MeV onward becomes allowed. Well, I can just briefly mention, I have just 1 minute left, that there is no fundamental principle ensuring the absolute stability of dark matter particles so long as its lifetime is not exceeding 10 to the 25 to 27 seconds. Now, a possibility consistent with current observations and highly studied in terms of constraints is that a WIMP dark matter freezes out, becomes decoupled from the cosmic soup through weak interactions, but decays slowly in various channels very, very slowly. And in these cases, in a duospheroidal galaxy, they can produce electron-positron pairs and, as we have seen, lead to tangible radio signals at the SKA. And this is the region of parameter space where this red part cannot be at all approached, whatever be the situation. This part is ruled out and probed in 100 hours of SK in certain scenarios, and this is ruled out always. So I think I have just come to the end of my talk, and I end with this observation. A really good scientist is one who knows how to draw correct conclusions from incorrect assumptions. Thank you.
Well, it's a very interesting presentation. As a layman, in some rough sense, I am curious to know the following. In the earlier part of your slide presentation, I found that the size of the dark matter is greater than 5 times the size of whatever is known.
Not size of the dark matter. The contribution of dark matter to the energy density of the universe is something like 5 times or more.
Okay, sorry. I correct my statement. The energy contributed is 5 times.
Yes.
When to me somehow paradoxic, it is a paradox. When infinities are involved, I want to know how you compare two infinities, 5 times something or something like that.
No. The energy density of the universe doesn't have to take a so-called infinite universe into account. You take galaxy after galaxy and you study the content of matter in the galaxy as evinced from the luminous part of observations.
So-
and you look at the, for example, content of the corresponding galaxy as seen from the rotation rate of the galaxy. In most cases, these can be consistent only if they are 5 times.
So that means we are not dealing with total energies, some sort of density or something.
Because of another assumption.
Oh.
Going at a scale where galactic distributions can be assumed as continuous, that's called a cosmological scale.
Oh.
That is where the universe can be treated as of our present understanding as homogeneous and isotropic.
Oh.
So if that is so, then if something prevails here, then we find no reason to see that in this direction, if you go.
So directional properties.
Away, it will be very, very different.
So that means you are dealing with finite numbers there in a sense.
Finite we extrapolate through our faith in the idea of
Oh.
homogeneity.
No, I got a different idea because of the complexity of the problem. Thank you very much.